Hello. In today's podcast, we will be discussing chapter 15, which is called Precast Concrete and Framing System.
So with precast concrete, there's framing systems, and it starts off with the concrete elements being casted in factories, transported to job sites, and assembled as components. The advantages of this is that it always gives you a consistent quality. It's mainly moved around through machinery, and it provides faster construction, especially when with like bad weather situations. It also reduces the need for foam work. Next, there's certain types of precast elements for concrete, and there are slabs, which are used for floors, roofs, and they range between solid slabs for short spans and hollow core for slabs, and double T's for longer spans. Um, there's also beams, girders, and columns. They're shaped in L-shaped, inverted T's, and regular beams. These help support and help support slabs and help with structural depth conservation. And lastly, there's a precast precast concrete wall panels, which are used for load-bearing panels. These can be solid or ribbed, and some integrated insulation. Sorry. Precast wall panels can also be non-load-bearing for architectural purposes. On the left, there's different types of girders and concrete beams. Next is the assembly concepts. Precast slabs can be supported by either a skeletal frame, load-bearing wall panels, or a combination of both. These are locally manufactured and tailored to the buyer needs, and usually are cost-effective. On the next is lateral force resistance, which helps with structures resistance. It provides lateral force for resistance through shear walls, brace frames, or moment-resistant frames, as shown on the picture on the right. Pre-stressing, reinforcing steel, and fiber reinforcing. So these are the types of reinforcing and pre-stressing. Slabs, they're usually in slabs, T's, and girders are cast with pre-stressed steel strands for greater structural efficiency. These are usually harpened or depressed to give it more strength. Mild steel beers, welded fabric, and stirrups are often used for reinforcement as well. Uh, the next one is carbon fiber. So the advantages of carbon fiber is that it can replace mild steel for reinforcement, which improves the structure's efficiency. It requires less concrete cover. It is lighter and has better thermal performance, and its high tensile strength and stiffness contribute to stronger and thinner precast elements. Next topic is concrete mix and production. So for precast, the PSI ranges from 400 to 6,000. It also allows for quicker curing and faster removing from the forms. The load on structures and foundations can also be reduced by 20% by using lightweight concrete. These are usually used in slabs. For the column production, there's pre-tension columns, and which are columns that can be reinforced with mild steel or pre-tension strands. These columns are often cast, cast and shipped in multi-story lengths with corbels included to support beams or slabs. The corbels are cast onto columns by setting up additional forms or steel plate inserts. These support the beams or slabs of the column sides. Sorry. Next up is hollow core slab production. There's extruded, the extruder process, which for the extruder process is a stiff concrete which is pushed through a die to form the hollow cores. Openings are added after extrusion or curing. The next is wet casting process, which is a wet concrete layer is placed on the casting bed, followed by collapsible tubes or lightweight aggregate that form voids. The materials are removed after curing. And lastly is the slip form process. In this method, concrete is deposited with moving hopper, and tubes are used to create the cores. The process allows for more flexibility in placing embeds and forming openings. Next up is the process of joining precast members. There's various forms to connect these concrete members, and usually they're bolting, welding, routing, and bearing. The bearing are used to reduce the high stress points between concrete to concrete contact, and it also allows for the structure movement such as deflection, either temperature changes or expansion and contraction. And one of the last inventions or like upcoming improvements is seismic and post-tensioning innovations. Post-tensioning is usually used for bridges, girders, or shear walls, and it allows for controlled movement between members and can enhance the structural performance during seismic events. These are different types of bolts and um, in the process of being assembled.
We then explore the joining of precast concrete members. In these pictures, labels of concrete members are given such as dry pack route, bus tension, anchorage plate, pocket for tension jack, bearing pad, and core bow. Here, a post-tension structural continuous beam column connection is created by passing a tendon from a pocket in the top of one beam through the column to a pocket in the top of the other beam. The tendon is then anchored to a plate in one pocket as is tensed by a jack in the other pocket. In this next slide, more information is provided on precast concrete framing systems. Here, top hollow core roof slabs are supported on beams and are joined to a column with vertical rods. Something similar can also be used for floor beams that rest on core belts. Another example of uniting precast concrete members is represented here where the beams in this system of framing rest on concrete corbels that are integrally casted with a column. The smooth top hollow core slabs are detailed for use without topping. The first picture demonstrates weld plates that are cast into the column, and picture B represents beams being placed on bearing pads on the corbels, where a weld plate is cast into the top of each beam at the end. In image C, the image showcases short pieces of steel angle welded to the plates to join the beams to the columns. Smooth-topped hollow core precast concrete planks are placed on bearing pads on top of each beam. Grout is poured into the gap between the ends of the planks, uniting loops and reinforcing that project from the tops of the beams, reinforcing bars that are inserted through the loops, and lateral pieces of reinforcing bar that are grouted into the keys between planks. The result is a tightly connected assembly that supports an on-topped precast concrete floor or roof. Continuing on, the next slide demonstrates another representation of joining precast concrete members where topped double T floor slabs are supported by inverted T-beams in this detail. Reinforcing bars that pass through hollow tubes pass into the column, connect the beams and column. The side cast topping then ties all the components together and gives a smooth, level surface as shown in Figure C. This picture and this next slide represents a cutaway view of the top double T slab. The arrow points to a site cast concrete topping with welded wire reinforcing fabric bonds to the rough top of the double T's to form a composite structural unit. In this next section, we explore more information of the construction process. Filigree precast concrete is first explored where thin precast elements are used as a formwork for site casting of beams and slabs. Once the process is complete, composite structural action between the site cast concrete and precast units result in a unified, structurally efficient system. And since the precast units remain in place as part of the finished system, form formwork costs are much less in comparison to conventional site cast concrete construction methods. The picture to the right demonstrates this. The construction process for precast concrete framing is similar to that of steel framing. First, the structural drawings for the building are sent to the precasting plant, where engineers and drafters prepare shop drawings that show all the dimensions and details of the individual elements and how they are connected. These drawings are then reviewed by the engineer and architect for conformance with their design intentions and corrected as necessary. Then the production of the precast components proceeds, beginning with construction of any special molds that are required and fabrication or reinforcing cations, then continuing through cycles of casting, curing, and stockpiling. The finished elements, which are marked to designate their position in the building, are transported to the construction site as needed and are placed by crane in accordance with erection drawings prepared by the precasting plant. Sustainability is also a topic of discussion for this chapter. For example, precast concrete walls panels with properly sealed joints have low permeability to air leakage, which reduces building heating and cooling costs, contributing to good air quality. Additionally, precast concrete production also encourages the reuse of formwork, reducing waste. Precast concrete elements with high-quality architectural finishes also can reduce the need for volatile organic compound emitting paints. Additionally, wood and fiberglass forms can be used up to 50 times without major maintenance, and concrete and steel forms can be reused up to thousands of times. Lastly, concrete is not easily damaged by moisture and does not support the growth of mold. We will then discuss building codes on precast concrete. Precast concrete is non-combustible and can be used in any building code construction, as long as it meets the necessary fire resistance rating requirements. The fire resistance of precast concrete building frames and bearing wall panels depends on whether they are made of structural lightweight concrete or normal concrete, as well as the amount of concrete cover that protects the pre-stressing strands and reinforcing bars. Fire resistance ratings of precast concrete slabs elements can be increased by increasing the topping thickness or adding a topping where none was required. And lastly, in the last portion of this chapter, we explore the uniqueness that is precast concrete. Precast pre-stressed concrete structural elements are crisp, slender in relation to span, precise, repetitive, and finely finished. They combine the rapid all-weather erection of structural steel framing with the natural fire resistance of site cast concrete framing to offer economical framing for many kinds of buildings. Engineers and architects are comfortable with precast concrete in longer span building type, these including parking structures, warehouses, and industrial plants. In addition, though it doesn't happen too often, precast concrete is sometimes used to create public buildings of the highest architecture quality, both inside and outside. This here concludes our podcast in this chapter, and we'll see you on the next one. Thank you.